Well, dear students, in the last lecture, we have developed the concept of this enrichment factor and how to calculate the enrichment factor uh, for a lighter gas in the case of simultaneous diffusion. So this is the case of simultaneous diffusion. Let's do one problem based on this. How many diffusion stages are required if uranium-235 is to be enriched from 0.7% to 7% by means of gaseous UF6 diffusion process, right? So first you have to see the concept behind this theoretical concept, as all of you are knowing that this is the concept of simultaneous diffusion. So basically we have, because just reading the question, you don't have much information in the question how to do this question, because nothing is given, only uranium-235 is given and 0.7% and 7% is given. So until or unless you don't know the theory behind this question, you cannot do this question. So uranium-235 and 238, there are two naturally occurring isotopes of uranium, in which uranium-235 is 0.7% by mass and rest is 238, and 235 is a good feasible material and used in the nuclear reactors and atom bomb, right? So first you have to develop your concept, like we have prepared UF6 gaseous 235 and UF6 238. So we have to convert entire uranium sample into UF6 gaseous, and then we do the study of this simultaneous diffusion step by step, right? So here this is vacuum, and after opening this valve for certain time, again this is shut down, and then the next wall is open, and simultaneously we do this process, and this is done by some automated process. So see, this is T is equal to 0 state, and this is equal this is the first stage. So we can see that UF6 moles of UF6 235 by moles of UF6 238 diffused out in step 1. This means this is the ratio of moles of UF6 and 235 and UF6 238 after the diffusion of the first stage. So here this is the molar ratio, and this moles of NUF6 235 by moles of UF6 238, this is originally present here. So this is the 0 means this is original. This is the ratio of moles of UF6 235 and UF6 238 after the first stage of diffusion. Molar mass, square root of molar mass of UF6 UF6 238 by UF6 235, and this ratio is called enrichment factor. So we have already calculated, see here, enrichment factor 1.0043. So I am directly putting here the enrichment factor. So we can write here N UF6235 by N UF6238 0 into 1.004343, right? So this is equation 1. So this is after first stage. Similarly, second stage, we do second stage, third stage, fourth stage, fifth stage. So let it be after any stage, right? So many stages we can carry out this. So what we can write for the nth stage? So the moles of UF6235 by the moles of UF6238 is equal to the moles after n stages. After n stages, this is I have written first stage. Now after n stage, directly don't calculate one by one. You can directly calculate for the nth stage. N UF6235 by moles of UF6238 0 and 1.0043 to the power n. So this is the because in every stage the mixture is enriched by 1.0043 times with respect to the lighter isotope, right? So this one enrichment factor 1.0043 to the power n after nth what step, right? After nth step. Now see what is the initial consideration. Again read the question. Enriched from 0.7%. So 0.7%, initially this was 235 is 0.7%. So you can take 0.7 this. So what is this 238? Obviously this is 99.3. 99.3, right? So 0 and 1.0043 to the power n. And now what we want here, 0.7 to 7%, means we want here 7% divided by, this is 93% after n stages, right? So after n stages we want this. So I think it is clear. See, this is moles ratio. So if you take mass ratio is equal to the moles ratio, all of you are knowing. In the stoichiometry we have done so many problems related to this, that if you have mass ratio in case of mass and moles, see Na by Nb, moles ratio is equal to Wa by Ma whole divided by Wb by Mb, right? Wb by Mb. So here what left hand side you do the same thing and you do the same thing in the right hand side. So this factor Ma and Mb, they are cancelled out, right? So directly you can equate this, no problem. So or if you want, you can see here, I will do this. but it will take time. If you understood, then it is okay, and if you not, then you can see. See, moles of UF6235 is equal to mass 7% we want, so 7 by what 235 we have 349, right? 7 by 349, and this n of UF6238 is equal to 93 by 351, 352, 352. So this is after n stages. Similarly, for this, moles of UF6235 is equal to 0.7 by 349, and moles of UF6238 is equal to 99.3 by 352. This is original condition, right? So if you put here this value 7 by 349 by 93 by 352 here, and you have put here 0.7 by 349 here and 99.3 by 352 here, so all terms this is cancelled, so you will get this. So in this ratio, their molar mass means moles ratio or molecules ratio, and weight ratio, that is equal, no problem, right? So now you can solve this. So in this way your calculation becomes shorter. Otherwise you have to calculate first from mass percent, you calculate mole percent, then you are taking ratio. Obviously at the end you are getting the same because it is present in the both side, right? Left hand side and right hand side. Now we can divide this. 10.677 is equal to if we do all these calculations, then this is equal to 1.0043 to the power n, right? So this is the solution of this equation. Now we can find out this value of n. How to find out? Take the log for the both the sides. So log base 10, 10.677 is equal to n log 1.0043, right? So if you solve this, so you will get 1.02845, 1.02845 is equal to 0.001865, 18635 n. So n is equal to 552 stages. So this is the answer. So after 552 times, if you repeat the experiment, right, then you get the you can enrich the uranium-235 from 0.7% to 7%. Clear to everybody? Okay, good. Now see another question, similar question based on the Graham's law of effusion. Now see, pure O2 diffuses through an aperture in 224 seconds, whereas mixture of O2 and another gas containing 80% O2 diffuses from the same in 234 seconds, right? So suppose that we have a container and same size container. In one we have only O2. This is a reference, basically this is a reference, and here O2 and some other gas, some other gas is also, let the other gas is A, right? A gas, and this is oxygen gas. So so when this is open, so oxygen and A gas, A, both will come out. Molecules of oxygen as well as A will come out, right? And here only oxygen will come out. So this is reference and this is experiment, basically. Experiment, right? So here O2 is coming out only, and here O2 and some other gas A is coming out. I think not for same time, they have given different time. So rate of effusion of oxygen R of O2 is equal to let it be pure O2 diffuses. So let it be the volume of oxygen here, some volume of oxygen diffuses 224 seconds. So this is the I mean by 224, or we can say moles of oxygen coming out or volume of oxygen coming out, because T and P are same, so volume is directly proportional to moles, so hardly matters, you can take volume as well as mole. And here what is the rate of oxygen, you are right, you can write or rate of effusion of gas A or rate of mixture. So definitely you have to write here rate of effusion of mixture is equal to volume effused out of mixture divided by, this mixture have both A and O2 both, by 234 second, 234 second, right? So now you have comparison. This is reference, control, you can say. This is control and this is your experiment, right? So what we can write here, this is I mean T and P are constant, so this is inversely proportional to square root of molar mass of mixture, and this is that inversely proportional to square root of molar mass of oxygen. So from Graham's law, we can write rate of effusion of oxygen by rate of effusion of gaseous mixture is equal to volume of O2 by 224 divided by volume of mixture divided by 234. This is equal to molar mass of mixture by 32. This is equation 1, right? Molar mass of O2. Now see, this is given volume of O2 is equal to volume of mixture. It is given in the question. Given in the question. See, pure O2 diffuses through an aperture in 224 seconds, whereas the mixture of O2 and another gas containing air diffuses from the same in 234 seconds. Means the content which is coming out in both the cases is same. Content means moles, volume, whatsoever, right? So we can write from equation 1, 234 by 224 is equal to molar mass of mixture by 32. So we can solve this. 234 divided by 224 is equal to this, and 1.044. 1.044 is equal to molar mass of mixture by 32. So on squaring of this, so 1.044 multiplied by 1.044, 1.089, 1.089 multiplied by 32 is equal to molar mass of mixture. So multiplied by 32, 34.8. So molar mass of mixture, now we have 34.87. This is equation 2. Now see, molar mass of mixture is equal to, we can write here, molar mass of oxygen into moles of oxygen plus molar mass of gas A into moles of gas A whole divided by moles of O2 plus moles of A. This is the general formula for molar mass of gaseous mixture, right? So see, moles of O2 is directly proportional to, we can write volume of O2, and moles of A directly proportional to volume of A, as T and P are constant. So we can apply here Avogadro's law. So molar mass of O2 is 32, and how much percentage of oxygen is given? 80% oxygen. So 80% volume percent of oxygen. So here 80 plus molar mass of A into 20 whole divided by 80 plus 20, and this is equal to 34.87. 34.87, right? So this is equal to, we can write 3487 minus it's equal to MA into 20, right? So 3487 minus 2560927. So MA is equal to 927 divided by 20. 46.35 grams per mole. So in this way you can calculate the molar mass of any gas by using Graham's law of effusion. Okay, good. Well, see another application one more application of Graham's law, that calculation of degree of dissociation. So see, first we understood what is this degree of dissociation. So the degree of dissociation, basically degree of dissociation it is represented by alpha. Okay? Because you know, in the upcoming chapters you will have this term, you will get this term very frequently. So the degree of dissociation, this is represented by alpha. What is the definition of this? Fraction of molecules or molecules of reactant dissociates. Basically, alpha is a fraction, and if it is fraction means have no unit, right? One more important property of this, that this degree of dissociation, it is defined only in dissociation reaction, right? This can be defined in dissociation reaction. So defined in dissociation reactions. Now another question arises, what are dissociation reactions, right? So dissociation reactions are those reactions in which single reactant, means reactant is single, that is converted into two or more products. So reactions in which single reactant converted into two or more products like Cl2 gas gives 2Cl gas. It is a dissociation reaction. Similarly, PCl5 gas gives PCl3 gas plus Cl2 gas. This is also dissociation reaction. But reverse of this reaction is not dissociation reaction, right? Similarly, this is also dissociation reaction. So these are the certain examples of dissociation reactions in which a single reactant, this is the criteria, single reactant is converted into two or more products. Okay, so we can calculate alpha degree of dissociation for here for this Cl2, for PCl5, for this ammonium nitrite, etc. So all these are dissociation reactions. So what is this degree of dissociation? So we can take one example and understood this, how this alpha is defined. So suppose that we have PCl5 gas converted into PCl3 gas plus Cl2 gas. This is a reversible reaction, right? So reaction is not complete. At T infinite, the reaction is under equilibrium. Suppose that we have taken n mole of this PCl5, right? So at any, at equilibrium, suppose that minus x moles of this PCl5 are converted into, dissociated into PCl3. So this is plus x mole, and this is also plus x moles, right? At any time t, and basically this is the change. This is the change. And what is the final? So final is n minus x is the left, and here x formed, and here x formed. Mole and mole, and it is mole. This is final at equilibrium. At equilibrium. Everybody is getting? See? Now, use the definition. Fraction of moles dissociated. So, alpha is equal to moles dissociated, moles of PCl5 dissociated, moles of PCl5 dissociated divided by, right, initial moles. Initial moles. So from equation, how many moles are dissociated? X moles. X. And what is the initial moles taken? N. So X by N. Right. So this is what? Alpha. One more way to write this reaction, and alpha is same in that case also, that we can write here PCl5 gas gives PCl3 gas plus Cl2 gas, and n moles of this are given. So n into 1 minus alpha, directly we can write the equilibrium moles, and here n alpha and here n alpha, right? N alpha and N alpha. Okay. So this is the equilibrium moles in terms of alpha. In terms of alpha. Directly. Right. So this is another way to write the expression. Now you can find the alpha. You will get the same result as here I have written. Now if you want to find how many moles of this are dissociated, so see how many moles are dissociated, n into the c, you have to multiply this. So or you can write here n minus n alpha, right? So alpha is equal to n alpha by n. So basically you will get what? Alpha. And in terms of x, you can see this alpha is equal to what? X by n. If you want, you can put here and you will get the same result here, right? You can apply the concept alpha. Alpha is equal to x by n. So at the end you can prove that this expression and this expressions are same. See, alpha is equal to x by n, right, from this equation. So here we can put alpha is equal to x by n. So what we can write here, n minus n into x by n, right, and n x by n and n x by n. So n cancel. So what finally we get? N minus x, x, x. This is the equilibrium moles. So both the expressions are same, right? There is no difference. If you are writing directly in terms of alpha, then you have to write like this, right? And one more thing, suppose that if initial moles were not given in any question, So to explain alpha, you can take here 1 mole, here 1 mole. And from 1 mole, alpha is always defined with respect to 1 mole. So whether you are taking here n mole or 1 mole in your answer or in your calculation, there is no difference, right? So it is, sometimes it is advisable, because sometimes examiner will not give you the initial moles. So and you require that. So instead of taking n mole or a moles, you have to take 1 mole. And if you take 1 mole, your answer will not affect in such type of calculations, means in the calculation of degree of dissociation, right? So in this way you can calculate alpha. Now see how to use this Graham's law to explain to find the degree of dissociation. Hopefully all of you are clear what is alpha and how it is defined, right? This is very important formula, because in equilibrium we will get every next question based on this, right? So clear? Okay, good. Now see, suppose that we have a gaseous reaction. A2 gas, 2A gas, and it is taken in a container. And same size, another container is taken. And here some reference gas, like suppose that argon we have taken. A reference gas means this is control and this is our experiment, and this is called control. So here from hole A2 and A both were coming out, both are gaseous, and here argon is coming out, right? So by comparison of rate of effusion of argon and this gaseous mixture, we can calculate the alpha. See how. A2 gas gives 2A gas, and initial moles I have taken 1, or you can take, you are free, you can take n mole, end result will be the same. 1 mole at T is equal to 0, this is 0. So 1 minus alpha, and this is 2 alpha, right? This is T equilibrium, right? So this is directly, if you have taken 1 mole, so from 1 you can directly write alpha here. If you want, you can see here I have written 1 minus alpha, so multiplied by n, so here n alpha will be the product, right? So in this way you can write 1 minus alpha plus 2 alpha. So what is the average molar mass of mixture? See, the molar mass of mixture is equal to, we can write here uh, moles of mass of A2 plus mass of A divided by moles of mixture, right? So mass of A2 is equal to 1 minus alpha moles into molar mass of A2 plus moles of this 2 alpha into molar mass of A divided by total moles 1 minus alpha plus 2 alpha, so 1 plus alpha. Total moles at equilibrium. Moles at equilibrium is equal to 1 minus alpha plus 2 alpha. So this is equal to 1 plus alpha, right? So here 2 into MA is equal to, you can write MA2. So for simplification, if it is not same, then leave that. You can use this equation as well simultaneously. So here you can write 1 minus alpha into MA2 plus alpha into MA2 divided by 1 plus alpha. See, this is important equation, so I am putting this equation number 1. This you can use directly. Now I am simplifying this. By putting this, I am simplifying this equation. So molar mass of mixture is equal to this. So we can write molar mass of mixture by molar mass of A2 is equal to this 1 minus alpha plus alpha, so this is equal to 1 by 1 plus alpha, correct? 1 minus alpha plus alpha, so it is equal to 1. So we can write 1 plus alpha is equal to molar mass of A2 by molar mass of mixture. So this is equation 2, right? Now apply the Graham's law. Compare the rate of effusion of this mixture and rate of effusion of this reference gas argon. So rate of effusion of mixture by rate of effusion of this argon is equal to molar mass of argon divided by molar mass of mixture per 1 by 2. So we can write here R of mixture by R of argon square is equal to molar mass of argon divided by molar mass of mixture. So molar mass of mixture. This is equation 3. Now see, from equation 2 and 3, from equation 2 and equation 3, what we can write? 1 plus alpha is equal to molar mass of A2 by molar mass of mixture, and molar mass of mixture is equal to, we can write molar mass of argon, right? Molar mass of argon multiplied by, divided by this. So this will go into multiply R of mixture by R of argon square, right? So we can write alpha is equal to molar mass of A2 by molar mass of argon multiplied by R of mixture by R of argon square minus 1. So by using this equation 4, you can calculate the degree of dissociation, right? And if it is this type of relation is not given there, suppose that here if PCl5 gives PCl3 plus Cl2 is there, so leave here Ma2 and Ma, make this one equation, calculate molar mass of mixture from here, because you know molar mass of argon is known, rate is known, it is given in the question, it should be given in the question. So here from here equation 3 you can calculate molar mass of mixture, put here molar mass of mixture, and this is known, this is also known, so alpha you can calculate. So these are the different formulas which you can use to calculate alpha from the Graham's law, right? Now see molecular collision and mean free path. See, this is the last part of kinetic theory of gases, and this is very important as well. See, as you know, what is molecular collision? One collision we have already discussed, that is the collision with the wall of the container. Similar formula, a little bit difference is there, but similar formula we have for molecular collision. But what is molecular collision? We can define, it is represented by Z, and it is defined as the number of collisions, or you can say more precisely average number of collisions made by single molecule, single gas molecule molecule per second, and what is the unit of this? Obviously per second, second inverse. This is the unit for this, right? So when we are assuming this, that to calculate Z, we are assuming that one molecule is free and rest molecules are free. So this is with respect to that molecule which is colliding. Once both the molecules are moving, or all the molecules are in the moving state, then formula is same but the constant is different, right? So this is the molecular collision, or collision frequency, also sometimes it is referred as collision frequency. What is this mean free path? Lambda. It is defined as the average distance, mean free path. This is the average distance traveled between collisions, or between two successive collisions, we can say, between collisions is known as mean free path. Mean free path. What is the unit for this? The unit of length, centimeter or meter or angstrom, nanometer, whatsoever, right? Now see, uh, there is a relation between this lambda and diameter of the gas molecule or any molecule. So for liquids, if you see, for liquids, lambda for liquid molecule or matter in liquid state, it is less than, much smaller than the diameter of molecule. Diameter of molecule. So this is the reason why liquid molecules are always in, I mean, in the fraction of diameter. If they move, they collide with the neighboring molecule, right? So in liquids, this mean free path, the magnitude of mean free path is very less. But in gases, lambda for gases, this is much larger than the diameter of gas molecule. Diameter of gas molecule. So, if you take gas at a very low pressure in a container, suppose that if you are taking two molecules of hydrogen in a large container, it is possible that year to year, they do not collide with each other, right? Because this mean free path is so large and probability of collision is so rare between two molecules that it will take years, or it may immediately collide. Nobody knows, right? But it is sure that lambda for gases is much larger than their diameter of the gas molecule, right? So if you see, there is a relation between z, lambda and average speed. So you can write one relation: u average is equal to lambda into z. This is very important relation, right? So if collision frequency is given, lambda is given, or u, if you have u average and frequency, collision frequency, or value of z, then you can calculate the mean free path from here. And one very important point is that this z and lambda, z and lambda both depends on depends on uh, collision cross section. Collision cross section sigma, and this is equal to pi into d square. I am not writing here that z and lambda both only depends on this collision cross section or this sigma, but they both depends on this collision cross section. What is d here? D is the diameter of gas molecule. Now I am showing you one figure and try to explain this collision, right, and collision diameter or collision cross section. So see, this is see, this is a molecule which is taken into consideration. This is diameter of molecule from here to here. This is D. So those molecules only collides with this molecule, center of which molecule lies in this cylinder, right? This D is the diameter. So swapping volume, you can say in 1 second what pi d square into u. This is the volume covered by this single gas molecule. So those molecules of which center lie in this cylinder, uh, they will collide with, and the center of those molecules away from the cylinder, they will miss the collision. So this is the collision, basically collision diameter. This is a cylinder basically. So D is same whether you are taking from this side or this, all this D is same. So this D is the diameter of the gas molecule, and this collision cross section sigma is basically a variable, we can say, collision cross section, which is very important, and this Z and lambda both depends on this. So if you remember what formula I have given you for the collision with the wall of the container, that is equal to Z is equal to 1 by 4 N by V uh, into U average into area is specified. So this formula already all of you are knowing. This formula all of you are knowing. Now see here, there is a difference between ZW and this Z. So this Z is directly proportional to again N by V. N by V. Again directly proportional to U average. And in place of A, here this collision cross section will come. Collision cross section will come. See, in place of A, this collision cross section will come. That is the only difference, and difference of this constant. And see here, we are considering here that the molecule is colliding with the fixed wall. So 1 by 4, there is a constant. Here constant is something different, and that is root 2. So root 2, which is experimentally determined. So Z is equal to N by V U average, and this pi d square you can write. So this is equation 3. So this is the molecular collision is given by this formula, equation 3. And now you can write here that this molecular collision Z is at given temperature, you can say Z is directly proportional to P pressure, because you know this N by V, this is called number density, and number density is equal to P into Na by RT. Na is constant, R is constant, and if temperature is constant, T constant, if T is constant, so Z is directly proportional to P, means collision frequency increases with rise in pressure if other variables are constant, and Z is inversely proportional to the square root of mass, molar mass of the gas, molar mass of the gas. But this is true only when the sigma is what? Same. If sigma is not same, then obviously this Z depends on sigma. Collision cross section. More the diameter, more the, bigger the size of molecule, more the probability of collision. So if sigma is same, collision cross section for two molecules is same, then we can generalize this, that collision frequency will directly increase with pressure and decreases with what, molar mass, right? And for sigma it is directly proportional to collision diameter, it is directly proportional to. And if other things are same, pressure is same, and molar mass means same, gas is there, means if all other things are same and you are comparing different gases, so see this sigma, if different, they have different sigma, then Z is different. More the value of sigma, more the value of Z, right? Now see, from here, from this equation we can calculate the lambda. So lambda is equal to, we can write lambda is equal to, what formula we have written here, lambda is equal to U average by Z, U average by Z, and we have calculated this formula for Z. So U average by Z is equal to, we can write root 2 n by V, root 2 n by V, right? U average into pi d square or sigma, we can say. So U average cancel. So this is equal to, we can write 1 by root 2 n by V. See, this number density is so important factor that starting from this kinetic theory of gases and through Graham's law and this collision frequency, everywhere this n by V factor is there, number density, and we can write this sigma. So this is equation 4. So by using these equations, you can calculate these parameters and you can interpret their dependency, mean free path, right? Now you can say that the mean free path lambda is inversely proportional to what? P. N by V, denominator, number density. So this is equal to P into Na by RT, temperature is constant, so you can write this, and lambda is also inversely proportional to the sigma. Is there any molar mass term is here? No. So lambda is independent of molar mass of the gas. This is very important. So mean free path is independent of the molar mass of the gas. No. This will depend on the size. This will depend on the size, but this will not depend on what mass of the gas. How lighter is the gas, how heavier is the gas, that hardly matters for this. It depends on the size, because this C inversely proportional to the collision cross section means collision diameter, right? So these are the different interpretations, and definitely you will get the question based on this, right? So mean free path is independent of the molar mass of the gas, but it is inversely proportional to the pressure. If you increase the pressure, and logically you can understood this, okay, when you increase the pressure, molecules are come close to each other. Obviously the average distance traveled by the gas molecules between successive collisions is decreased, right? So this is all about mean free path, their dependency on different factors, and collision frequency, right? Now from the next lecture, we will discuss real behavior of the gases, and that is the last topic of this chapter.